Hello, I'm Gary Millett, and I'm going to talk to you today about power and energy in DC circuits. I call this topic number 9A. This is for electronics for technicians, the fall of 2022. So we've talked about some of this stuff already. In this slide, I say this material has been touched upon in the Sen gauge materials in Unit 2, which are pages 209 and 210, and in the topic number 5, which I called Ohm's Law, Work, Energy, and Power. That's my PowerPoint presentation, again, for topic number 5. So I'll review it here in light of the fact that we have covered basic DC circuit theory at this point in time. So again, power is defined as a rate of doing work or the rate at which energy is used. Power has units of watts or, more officially, joules per second, although we hardly ever would use joules per second. So you want to recall the kilowatt hour. You know, you may live with your parents or somebody else, or an apartment where somebody pays the electric bill. Of course, it's all part of the rent, I'm sure. And you might recall what's called the kilowatt hour. So the electric utilities charge consumers by the kilowatt hour. That's the number of kilowatts used per hour, which is actually the amount of energy one has used, not the power. Presently in Massachusetts, the rate is roughly 15 to 20 cents per kilowatt hour. Today is November 1st of 2022, and today utilities talked about the fact that electric bills might go up by 64% due to shortages of, the materials we use to produce energy. Of course, the 15 to 20 cents per kilowatt hour is just the cost of producing the energy. It is not the cost of delivering it, and that's roughly about the same amount, 15 to 20 cents per kilowatt hour for delivery charges. So actually, electricity in Massachusetts, my last bill was roughly about 36 cents per kilowatt hour. Unfortunately, that means that unless you have solar panels, having an electric car is a losing proposition right now, because the cost of charging the electric car is more than the cost of gasoline. Power in a DC circuit is calculated as being equal to the current in a circuit times the voltage across the circuit. So we see the equation here, power equals V times I. Power equations are much like Ohm's law equations in that we can manipulate them algebraically. So the equation for power is similar to Ohm's law in that it can be rearranged into 3 equations as I show here. The one I had in the prior slide, power equals V times I, is the primary equation, but you can also say that power is equal to I squared R. If I substitute what V is equal to in Ohm's law in there, I'll get I squared R. Or if I substitute what I is equal to, I'll get power is equal to V squared over R. So again, which equation one uses is dictated by what information one has. One might question, where does the power go in an electric circuit? So power provides energy to other systems. Where the power goes is all dependent upon the type of load that is having the power delivered to it. So here I kind of talk about this. If the load is some form of machine, that should be then the power is changed or converted to some other form of energy. i.e. a DC motor produces rotary mechanical motion. If the load is an audio amplifier, it delivers sound energy when it's driven by an audio source and it is connected to some type of loudspeaker. If it is an LED light bulb, it produces light energy. A resistive load just produces wasted heat unless it's supposed to be a heater. Here's a picture of a DC motor. So if I was to apply a DC voltage to that, we know that the rotor, the center, round thing that's coming out the end of the motor would spin, and we could do work with that. Here is a picture of an audio amplifier in the center and some tall loudspeakers that probably will cause your neighbors to complain about how loud you might play your music. Here's some LED lights, and the LED lights plug into AC power, but the AC power is converted to DC, and then the LEDs inside that bulb fixture luminesce, and it turns out that these LED lights are extremely more efficient than incandescent light bulbs, and even the ones that were the squirrels, or swirly ones, whatever you want to call them, the CR, well, whatever they are. So here's an electric space heater, and winter coming on, sometimes we use these in lieu of other forms of heat energy. So that in this case, we like to have the electricity go, the power go for heat. So this slide says energy sources and concepts. Energy may take many forms. The following slides show the different types or forms that energy might take on. And so here we have two basic forms of energy, and they are kinetic energy and potential energy. So kinetic energy is the energy of movement, whereas potential energy is stored energy. So you go down a little bit and it says energy comes from moving, and there's thermal energy, that's the energy of moving particles or heat. Mechanical energy, the energy of objects in motion. Electrical energy, energy of particles moving through a wire, which would be electrons. And magnetic energy, and they use the term energy causing push or pull. Magnetic fields will cause things to be either pushed or pulled. On the right-hand side, potential energy is stored energy, and energy is stored to be used later. And we have chemical energy, energy stored in food and fuel. Elastic energy is energy stored in objects that are stretched. It could be a spring, for instance. Nuclear energy is energy stored in the center of particles. Atomic fission can provide you energy. Fusion we're still working on, where you fuse atomic nuclei together. Gravitational energy, energy stored in an object when it is above the Earth's surface. And in the middle there we have sound energy, a form of energy we can hear, and light energy is a form of energy our eyes can detect. So as we have evolved, we have developed senses which can detect sound energy and light energy. So here's an equation for kinetic energy, the energy of moving mass. You see on the left-hand side, Ke, or kinetic energy, is equal to 1/2 mv squared. M is the mass of the object, and v is the speed squared. Potential energy, energy to the position of a mass. I show in this diagram two red objects. Gravity is pulling the object on the left-hand side down, and the distance it is above gives rise to so much potential energy. On the right-hand side, I've got a red object which might only go down to, say, landing on a table. And again, it has less potential energy because it turns out the distance it would fall is less than on the left-hand side. So potential energy equation is E sub P is equal to mgh, where potential energy is E sub P, m is mass, g is gravitational field strength, and h is vertical height. So it all depends on the value of gravity. So here's a little slide that shows, if you're into riding down roller coasters, types of energy potential converted to kinetic. So it shows a little coaster car up there in the top left. It's got very high potential energy, but low kinetic energy because it's probably just gone up a ramp and now it's just starting to accelerate. As the coaster car loses height, it gains speed. Potential energy is transformed into kinetic energy. As the coaster car gains height, it loses speed. Kinetic energy is transformed into potential energy. The sum of the kinetic energy and the potential energy is constant. So in the valley there, you see minimum potential energy, maximum kinetic energy, probably going the fastest. Goes up a slight hill again, slight incline. It's got low potential energy, high kinetic energy. Other types of energy, here's thermal energy. Thermal energy is the relations between temperature, heat, and thermal energy. So temperature is a measure of the average kinetic energy of the individual particles of a substance. Thermal energy is total energy of all the particles. And heat is the thermal energy moving from a warmer object to a cooler object, trying to reach thermodynamic equilibrium. So it turns out in these little diagrams, you see a thermometer there. It's cold, not much thermal energy. You see the guy panting up on the top right, it's hot. Temperature is very high, so us humans can't handle it too well. The bottom diagram shows it says longer arrows mean higher average speed. So if something hotter, it turns out that the molecules will vibrate more and over a longer paths. Now, nowadays we're very much into this idea, the non-renewable energy idea. So this slide shows various forms of energy sources that are non-renewable, i.e. fossil fuels, nuclear, and so forth. So if you take a look there, there's a little picture. There's a oil and gas rig out in the water, power stations. Notice the power station in the top right. Turns out it might be a nuclear power station, and we need nuclear fuel for that. And of course, the problem is that once the fuel has been used for most of the nuclear power plants that have been built in the last 40 years, you have to store that spent fuel someplace. That's a difficult problem. Fossil fuels, things like oil and coal and so forth, they take and they do a lot of pollution. So we generate our electricity from, fossil fuels like oil. We used to in New England use coal. We don't anymore. None of the power plants use coal. We use a lot of natural gas, but in the wintertime, if we run out of natural gas, it turns out we don't use it for producing electricity. We revert back to oil. And oil is a dirty form of fossil fuel. My last slide. Oops. Where's my last slide? I guess I got to use this. My last slide, renewable energy. It turns out that this shows the types of energy sources that are renewable and clean. So some of these things you see is the sun that's shining there, the solar energy, biomass energy. So again, solar energy from solar arrays on people's houses and so forth. Tide energy, wave energy, hydrogen fuel cells, hydroelectric energy, wind energy, and geothermal energy. All these things are renewable and they don't pollute. And finally, the last slide, the future of energy sources. Renewable energy at this point is not reliable. Solar is only available when the sun shines, and wind power is obviously dependent upon the wind, which doesn't always blow. Therefore, one of the biggest challenges is to be able to store solar and wind energy for use at a later time. That usually would mean we'd have some type of batteries or hydroelectric power or something like that, where we store the energy for later use. How this will play out is very uncertain today, and actually we're going into the winter of 2022, extremely uncertain when geopolitical events cause us to, be at the mercy of other countries for our fuels to produce electricity. So that's it for this one.